45 minutes and lunch. It's okay, of 40 minutes and lunch. Okay, you're tired, right? You look tired, right? Okay, this is a tutorial lecture, but I need to go ahead 10 more minutes in theory. And later I will do one of the things that I promised you to do in the previous lectures, right? It's just to finish this more theoretical part. If you remember, yesterday we were talking about, okay, we had pions, and then we said, what happens if we include also nucleons in the business? And then I think that Xiang-Kun has shown you that this object here, psi bar, psi tilde, psi, is a chiral invariant, right? Did he? It's a chiral invariant object. Okay, so I have a blackboard. I asked Xiang-Kun to show you that psi bar, psi tilde, psi is invariant under vector and also under axial transformations. Then it's a chiral invariant object. Okay? And this psi tilde is just, okay, this psi tilde is just f pi v squared, and v is just v is just e to the I gamma 5 tau 5 over twice f pi. Okay? So this object now is about Dirac degrees of freedom, because you see that here you have gamma 5. Okay? This object contains pions. And the fact that you have the Pauli matrix is just because we are doing just SU2, right? We are talking about pions and nucleons. And psi, it was the proton neutron, it was the nucleon doublet. And then, well, I think that we discussed yesterday, you can do a vector transformation, which is the first line there, or you could do an axial transformation. And then you should always bear in mind that in the axial transformation, you have always something related with the Dirac space, because you have the gamma 5. Then, if this object is a chiral invariant, then automatically, well, I have pions here, right? I have this trace d mu u dagger, but I can include nucleons, and I can include easily. I can always include the kinetic term and minus g psi bar psi tilde psi. Okay, this is chiral invariant, and then you may wonder what happens with this term. But we have discussed several times that the kinetic term is chiral invariant, right? It's no problem. Under vector transformation is trivial, right? Because under vector transformations, I don't have any complication in the Dirac space, and I have, well, I have psi goes to transform like e to the minus I tau theta over 2. Well, okay, e to the minus tau theta over 2 times psi. Okay, this is psi prime. And then psi prime bar is going to be psi bar e to the I plus I tau theta over 2. Then automatically you have a vector transformation. The vector transformation ignores the Dirac space. We are talking about global transformations, and then you have psi bar psi is an invariant because you have trivially that psi bar prime psi prime is the same thing as psi bar psi. Okay, it's trivial. Under an axial transformation, your life is a little bit more complicated because the axial transformation involves the Dirac space because you have the gamma 5 matrix, right? And then you may wonder if this is still true, right? But I think that we discussed what we can do once more just to make it clear. If I have here a gamma 5, then what happens? If I do psi dagger prime, so I take dagger here is psi dagger e to the I plus I tau theta gamma 5 over 2. Okay? Now if I multiply by gamma naught here to get psi prime bar, then I need to multiply here by gamma naught. And because gamma 5 anti-commute with all the gammas, then what you have is that this is psi bar e to the I minus eta gamma 5, okay? So now you see that this object now is not going to be invariant under an axial transformation, right? And we have discussed this thing many times, that the mass of the fermions is a problem for an axial transformation, but the kinetic term is not psi bar psi. The kinetic term is psi bar gamma mu. You have a gamma in between, right? You have a gamma in between. So then what you have is, well, I didn't mention the gamma in the vector case because the vector transformation doesn't involve Dirac, right? So then you have psi bar prime, then you have this factor e to the e minus I, then I have the gamma mu, and then psi becomes, it transforms also with e to the minus, okay? And I have psi. But now, if I commute this factor with the gamma mu, it becomes e to the plus, and it cancels, right? So there is no problem. So we have a Lagrangian involving pions and nucleon that is chiral invariant. Okay? Very good. Okay. Okay, so let me just pay attention to the baryons. And okay, so we have psi bar I gamma mu psi minus G psi bar, and then this sigma tilde is F pi V squared. So let me put here minus G F pi B squared. B is not it doesn't have anything to do with vector. It's just a matrix that I call V, right? B squared, and here I have psi. Okay. Now what I am going to do is I am going to do a unitary transformation, right? So I am going to define a new field for the nucleus that I am going to call psi omega. That is going to be just B times psi. Okay, and B, this unitary transformation is precisely what I have here in sigma tilde, right? Okay, so what I have. So then it's just what is written here. What we have is, okay, psi is going to be psi bar omega, and I am going to have V dagger. I am going to have E gamma, E d mu, no, sorry, E gamma mu d mu. Now I am going to have minus g f pi, exactly. And then we had v squared. And then psi is just v daga psi omega, right? So then if I continue, then what I have is psi bar omega v daga e gamma mu d mu yeah v daga psi omega, and then this is easy now, right? This is very easy now. Okay, can anyone tell me what is this? What is this? It's a mass term for your nucleon. And the mass is being proportional to F pi. And F pi, I remind you that it was what? The Beck. It was the vacuum expectation value of the axial charge. Sorry, not the axial charge, sorry. The vacuum expectation value of the field of the theory that doesn't annihilate, that takes a non-zero value in the vacuum just because axial charge does not annihilate the vacuum, right? So then, with this spontaneous symmetry breaking of the axial current, I am able to give masses to the nucleons, right? Because it's proportional to F pi. And then you have to work a little bit more with this. But this is going to give you interactions between what? Between nucleons and pions, right? Because you have here your nucleons, okay? You have here your nucleon lines, right? You annihilate, you create, so this is your nucleon line. And then in V, you have the pion fields, right? So then automatically this is going to give you interactions between nucleons and pions, okay? And everything is just determined by F pi, the nucleon mass, and by requiring chiral symmetry, right? Because I have written a Lagrangian involving nucleus and pions that is consistent with chiral symmetry. Does it make sense? And that, okay, so I am not going to continue more, but then it's easy, okay, you have here, okay, there is something here that I have. Okay, so then here you have a derivative, then you have to do this thing, be a little bit careful, and what you get is the last line in the, You may remember what this psi is. Well, actually V, I just include the notation because if you look at any paper of chiral symmetry, it will appear this psi for you. I mean, this is just, V is just psi plus psi daga divided by 2, the plus gamma 5, psi chi minus chi daga divided by 2, okay? So it's just V. So you just take the derivatives and you just do your keeping, and then you have two terms. It appears two terms. One here that is in the, is like defining a new covariant derivative, right? It's like defining a new covariant derivative, okay? And you have another here that that is contracted with the axial current because you have gamma mu, gamma 5. And this is chiral invariant. And then I have made a PR already, the nucleon mass. okay, which is just GF pi, okay? So what can you do? You just do an expansion in the number of pion fields in the same manner that the Xian Kung has done in the previous lecture, and then you just, it's a bit tedious, but you have to sit down and do it. It's nothing, right? You just do it, and then if you just neglect 4 pion fields, right? So you just keep 2 pion fields and 1 pion field and 2 pion fields, you get 2 terms. The first one is Weinberg-Tomosawa. Weinberg-Tomosawa. Tomosawa. And this 1 minus 4f pi squared, psi bar, so nucleons, then you have gamma mu, you have tau, and you have psi cross d mu psi omega. Okay? This is called Weinberg-Tomosawa. You see that they have by free, well, it's not by free, but this is isospin invariant, right? I have constructed, this is an isospin, this is an isospin scalar, right? A scalar, because I have an isospin vector and I multiply, I take the scalar product with an isospin vector, so then automatically I am being consistent with isospin symmetry. That's by definition, because I have require chiral symmetry, and then the vector part of chiral symmetry is isospin, right? What is that is given to you? This kind of terms. You have 2 pions that couple to a nucleon. This is Weinberg-Tomosawa. And actually, the 2 pions that you have here are coupled to some isospin. Which isospin? 1. Because you see that I am constructing a vector. I am putting 5 cross 5. Well, 5 cross 5 will be 0. It's 5 d mu 5. But in the internal, in the isospin language, is 5 cross 5. It's a vector, right? So, so this involves pions coupled to isospin 1, right? Actually, in some sense, okay, that you could see something like that. You could think about this something like that. It's like the nucleons, they couple to a row, and then the row meson decays into 2 pions, right? Because the row is an isobector, okay? The another term. In another term, what I have is the coupling of the nucleon with just 1 pion, right? Because I have only 1 pion line. So then what I am obtaining is this coupling. Tell me. Yeah. So then it will be the, well, no emitting. I mean, is nucleon going to nucleon row, because I have to conserve the baryon number, of course, and then the row decays into 2 mesons, right? But in principle, I mean, in my theory, I have the nucleon and 2 pion interactions, right? And that's it. What happens, I mean, I just mentioned the row meson because if you go to higher orders, then appear contact terms, and these contact terms can be obtained just assuming something that is called resonant saturation, and then there it appears the row meson. It just, I want you to, okay, to know that if somebody talks about Weber-Tomasawa, okay, the raw meson plays some role, right? But in my theory, I don't have raw mesons. I only have pions because I am doing an effective theory where I am integrating all the degrees of freedom which are heavier than pions, right? So actually, I don't know if, okay, look, what I am doing actually is, okay, in this kind of diagrams where in principle you have a heavier degree of freedom, which is the rho, because the mass of the rho is 770 MeV, is 770 MeV, 770 MeV. Okay, so here I have a propagator, right? Anyone knows how the propagator is? It's a spin one field. I don't know how much you know about quantum field theory. But somebody will know how is the propagator of a spin one field. The propagator of a photon will be something like that, no? Because a spin one field should have a Lorentz index, right? But the photon is massless, while the raw meson has mass, right? So then the propagator is and Q is this momentum transfer. Okay, what happens? What happens if I am in a energy regime, in a momentum regime, where all the momenta that appear are much smaller than the raw mass? Because I am doing a theory only for pions and I am taking only the leading order, right? So I am just keeping very low energies. If all the involved momenta are much smaller than the raw mass, then I don't have this, and that becomes a contact. Right? I don't know if this is useful or not. Okay, so I don't want to make any point with the. Okay, so this is the nucleon-nucleon pi coupling, and that gives you have heard about one pion exchange potentials in nucleon-nucleon, but the only thing that you have to do is you have another two of these two vertices give you the one pion exchange potential, and that's very well defined, and everything in principle is determined by chiral symmetry, right? Here, well, I need two inputs, right? I need the nucleon mass and F pi, okay? Because in an effective theory, you have constants and you don't know the value of the constants. One thing, because I know that Fenkun has told you many things about parity and angular momentum conservation and things like that. What's the spin parity of the nucleons? 1 plus, 1/2 plus. The spin parity of the nucleus is 1/2 plus. The spin parity of the pions? 0 minus, right? And then of course, I want to conserve spin parity. So how does it work? P wave. The nucleon and the pion are coupled in P wave, because if you have a P wave coupling, then you have 1/2 plus. So if we just pay attention to parities, we have the intrinsic parities plus, minus, plus from the nucleon, minus from the pion. But if they are coupled in P wave, then we have an additional Yes, L equals 1. P wave means L equals 1. So I can think that the nucleon emit a nucleon and a pion, but these two guys should be coupled to L equals 1. Otherwise, it doesn't work, right? So that involves P waves. And P waves means that this coupling is going to be 0 when the momentum of the pion is 0, right? Because then you cannot have P waves. While here is different. In the Bember-Tomosawa is different. I have 1/2 plus, 1/2 plus, and I have 2 pions. And the intrinsic parity of 2 pions is plus. So, and that is going to be important for the rest of the lectures. Here, you just get the general idea. Here you have P wave interactions, while in the Bember, here. While in the Bember-Tomosawa, you have the possibility of S-wave interaction. You may have 2 pions coupled to S-wave, right? Okay, does it make sense to you? The rest of the lectures, I will pay attention only to this Bember-Tomosawa thing, okay, to this Bember-Tomosawa. There is one thing, you see there that I have GA. I have put a new guess in the discussion. I was telling you, I have only nuclear mass and F5, but now I am putting GA. Why is that? What I have shown you is that the sum of the two terms is chiral invariant. So then in principle, if I modify the strength of one of the terms by an arbitrary factor GA, then in principle, I may be spoiling chiral invariance. I may be breaking chiral invariance. That's bad news, right? In principle. Of course, I don't have time to do that, but the message is that the sum is chiral invariant, but each of the individual terms is chiral invariant by itself. That allows me to introduce a different strength for the second term. This is what is called GA, is the axial coupling of the nucleon that you may have heard, right? The axial coupling of the nucleon. Then I might introduce this without spoiling, without breaking chiral invariance, okay? And this value GA takes experimentally is the order of 1.26. So the prediction of KPT, a leading order, is I was getting something like 1, so it's not too bad. And then I don't know if you have ever heard about Goldberger-Treiman relation. No, but it's just here. The Goldberger-Treiman relation is just that is telling you that this coupling, which is the G pi n coupling, is related with F pi and with the nuclear mass. Okay? This is Goldberger-Treiman relation, which is what I have here. What happens is that I should multiply by GA. So during these lectures, I have tried to introduce you a little bit what chiral symmetry is, right? I don't know if you have followed, well, some of you already knew about these things. In the next lectures, because I was asked to talk about hadron structure and talking about some exotic hadrons, right? And then I choose to talk about baryons. Then, and I told you the first day, I will focus in the lambda 1405. That really is understanding the lambda 1405 really represented a revolution in the field. But the lambda 1405 is going to be dynamically generated, and I will explain you what the hell this thing is, by the Bember-Tomosawa interaction. But the Bember-Tomosawa interaction, because the lambda 1405 lambda means that it has a strangeness, right? So I should go beyond nucleons, right? I should go beyond SO2. I should go to SO3, right? So then I should do a construction, but in 3 flavors instead of 2 flavors. But the idea is the same thing. The idea is similar, right? The idea is similar. You just work with 3 flavors and you just construct something that is chiral invariant. And then, okay, because I have in SO3, so I am going to have an octet, right? And then I am going to have the neutron, the proton. This is strangeness 0, but then I will have strangeness -1, and here I am going to have the sigma 0. No. Excuse me, sigma minus. Here I am going to have sigma 0. Here I am going to have sigma plus. Here I am going to have lambda. Here I am going to have cascade minus, and here I am going to have cascade 0. Okay, so this is this octet with a spin parity 1/2 plus. And in this line in here, I have a strangeness -2, right? So then this is what I can construct with the U, D, and now the S quark. Okay, so neutron and protons are constructed out of the U and the D, right? Is -1, -2 instead of +1, +2 because for some convention the strange quark carries strangeness -1, okay, in some convention. And here what you have is, okay, something that you can construct with the, so you may have UD coupled to isospin 0, or you may have UD coupled to isospin 1, right? And then, in addition, you have the strange quark. Okay, so I think that some of the discussions that I think that Fenkun has made to you. Okay, if I have UD identical particles, because I am working in SO3, they have isospin 1/2, right? So then, if they are coupled to isospin 0, the wave function is what? Antisymmetric. Very good. If they are coupled to isospin 0, the isospin wave function is antisymmetric. Okay, because I am talking about ground states, the orbital angular momentum should be 0, right? Because I am talking about ground states. So the orbital angular momentum is going to be symmetric. Okay, so then what happens with the spin? Should be symmetric. Should be symmetric. Why? Because the total wave function should be antisymmetric. No. We are forgetting the color, and the color is antisymmetric. Thank you very much. I was puzzled because I was about saying, okay, the lambda has, I was really puzzled, right? I was forgetting the color. The color is always antisymmetric, right? Well, sometimes what happens is that you ignore the color, and then you just look for symmetric wave functions, right, in flavor. But then you have, it's antisymmetric, so that guy should be also antisymmetric. So in the flavor, subspace is a symmetric wave function, right? So that means, antisymmetric means that the spin is 0. So then you have a structure where you have the, more or less, you have the S and you have the D, and they are coupled to isospin 0 and spin 0, okay? And this is, I introduce you the lambda. more or less. Yeah. Actually, I saw in the blackboard when I came in that there was the lambda c, right? The lambda c is the same thing. You just replace the strange by the chunk work, right? What happened with the sigma? So I can couple the UD to asymmetric representation in the spin space. Again, because it's the ground state, angular momentum is going to be 0. So then it's symmetric, right? So then I need that the spin should be symmetric. So then what happens is in the sigma, you have I equals 1, and the light degrees of freedom, if I start talking in terms of heavy core spin symmetry, are coupled to spin 1. But that's the reason why you see that they have 3 sigmas, right? Because it's a triplet, because they have isospin 1, right? And finally, what is the isospin of the cascades? It's easy. I mean, it's in the plot. 1/2. Why is 1/2? Because this guy is SS. SS what? D, and this is SSU. Right? SSD and SSU. Okay, so then instead of working only with neutrons and protons, I am going to work with neutron, protons, lambdas, sigmas, and cascades. And then instead of working only with pions, if you look at the another big matrix, I will have to incorporate in the game, in the discussion, pions, kaons, antichaons, and the eta meson. Then with these elements, I should construct, one can construct a chiral invariant thing that, well, it looks more complicated, but Wimberto-Bosawa is this, which is similar. V bar, V, gamma mu, and this is a commutator. That commutator is something that is like, is the generalization of, I don't know where, I wrote some place, phi, yeah, phi cross d mu 5, right? Is the anticommutator. So, and then in principle, I know everything, okay? I think maybe tomorrow we have in the first lecture, because it's already 1 o'clock. If I begin anything, it will take 20 minutes. Perhaps in the first lecture, instead of going ahead, I will do some exercises for you, right? But let me just talk 5 more minutes about the lambda 1405. Why I am interested in the lambda 1405, right? Lambda 1405. The mass is, in principle, is 1405 by definition, right? What's the mass of the lambda hyperon? I mean, you just told us the other day. Well, the ground state in the lambdas, well, maybe 6, but when I study, it was 5, 5 something, right? In the PDG appears like 1115, no? I don't know. So this is the ground state. 1/2 plus. The lambda 1405 is 1/2 minus. Okay. This is called a P-wave resonance. It's a P-wave resonance. Why is called P-wave resonance? Because in principle, the thing is you may have K bar. Antichaons, they have the antichaons, well, antichaons, they have the S quark. Kaons have the S bar quark. So antikaons are U, S, U, and U bar D bar, where kaons are S bar, U, and D. Okay? So then in principle, you may have K bar nucleon, and then if you do K bar nucleon, you have 1 unit of strangeness, right? But what happens with the parity if I don't do anything? What is the parity of this? Hmm? Sorry? Yeah. Okay. No. Everybody agree, but no. What is the intrinsic parity of the kaon? Kaon is in the octet, right? And nucleon? So I don't need P wave. And then you will wonder why it's called P wave. Let's come back to this picture, the quark model picture. Because I have potentials for the quarks, I can compute this thing, right? If I put everything in S wave, then I get 1/2 plus, right? But how can I get 1/2 minus? Putting some L equals 1 component, right? And that's the reason why this resonance is called P wave, right? Because you need to put either L equals 1 here, or if you don't put L equals 1 here, then you should put L equals 1 here, and then the parity changes, right? For heavy quarks, I guess that Fenkun told you, the spin parity of the light degrees of freedom is well defined, right? So then if I have a charm quark, I can tell you, okay, this is a problem where I have L equals 1 in the light degrees of freedom or L equals 0. But in the case of the strange, you may have mixings between both configurations, right? You may have mixings between situations where you have the unit of angular momentum here, because these are mathematical states, right? So this is what, I don't know if you have worked with, I don't know if you have ever worked with, exactly, lambda modes and row modes. People working in quark models, they distinguish between excitations of row mode or of row type or excitations of lambda type. And row doesn't have anything to do with the row meson. It's just one way to talk about. When you have 1 unit of angular momentum here, this is lambda mode, and when you have 1 unit of or maybe I am getting the another way around. And this is the lambda mode, okay? And these are mathematical states. The real state will be a linear combination of the two things. But in the heavy quark limit, they decouple, right? But when the heavy quark limit means that instead of a strange, you have a charm. What's the problem with the lambda 1405? That, okay, people working in the constructor quark model, they have, okay, they study the proton and the neutron. They tune the masses of the constructor masses of the U quarks, the D quarks. Also, they look at the hyperon, the ground state, 1/2 plus, the ground state, the 1/2 plus, just to fix the mass of the strange. They have a quark potential, right? Just one gluon exchange and with some parameters, and they get very well. They get well, quite well, all the members of the 1/2 plus. However, when they try to get the lambda 1405, which is just to add 1 unit of angular momentum, they fail. They fail in the sense that if they don't fine-tune the parameters instead of 1405, they get something above 1500. 1500. So 100 MeV. In any model, there are always parameters that you can fine-tune just to get any number you wish, right? But it's not natural. And that is indicating that perhaps this resonance, it doesn't have a structure of 3 quarks, right? It may have a structure, and what I will tell you is that, okay, I'm going to generate it just by looking things like that, scattering of these things. And here you have the nucleon. Okay, nucleon, for instance, and now I promise I finish. Okay, so I have nucleon, for instance, the proton, UUD, right? Kaon, S, U bar. I have done K minus proton because the lambda doesn't have charge. How many quarks do you see here? I think that the last thing that Fenkun told you about was about pentaquarks in the chance sectors, right? But this is a pentaquark in the strange sector. If I show you that I can generate the lambda 1405 from the K bar N interaction, actually, yes, count. You have there 5, a structure of 5 quarks, right? Which is allowed, right? Because at the end, what is the nice thing about pentaquarks is that when you have 4 quarks on a Q bar, you can get a singlet in the corner space. Otherwise, you are into trouble, right? So, of course, people working in quark models, if they incorporate these degrees of freedom, they can get better results for the lambda 1405, right? Because in nature, all the possibilities that could happen happens, right? So everything will be a mixture of any picture. But I will show you that just with Ben-Tomosawa and doing a resumation that I thought that because to generate a bound state, or I need to go beyond just the potential. I need to solve something like the Schrödinger equation, right? That or the Lyman-Schwinger equation. That means that I need to do a full resumation. Then I will find poles, and one of these poles, I will find states, and one of these states is going to be the lambda 1405, very naturally. And actually, we'll show you that there is not only one lambda 1405, that the chiral structure tells me that there are 2. There are 2 masses, 2 states around this energy. Okay, thank you very much, and I'm sorry that it was late.